The quantum numbers. There are 4 quantum numbers. Number 1. Principal quantum number. It was the consequence of the study of the line spectra of hydrogen gas by Niels Bohr, where it was assumed that electrons cannot remain in any orbit around the nucleus, but only some quantum selected orbits were chosen such that the angular momentum is an integral multiple of h bar, where h bar is h divided by 2 pi, where n is the principal quantum number, which has the following features. Principal quantum number specifies the principal energy level of the electron, which was called shell. It can have integral values like 1, 2, 3, 4, or they may be written by capital letters K, L, M, N, etc. Charles Barkley, in a spectroscopic experiment with atoms hit by high-energy electrons, studied the X-rays emitted. He named the highest energy X-ray with the letter K and not by the letter A because he wanted to be certain that he kept room for later discoveries, and he wasn't sure that this X-ray will be of the highest energy forever. This highest energy X-ray was a result of the innermost electrons of the atom, and so naming of shell started with the letter K. The more the value of n, more is its energy. The energy is given by this equation for hydrogen-like atoms with a single electron. The maximum number of electrons that can remain in a particular energy level is 2n square. The more the value of n, the greater is the distance of the electron from the nucleus. Number 2. Azimuthal or angular quantum number. It was the consequence of fine spectral analysis of line spectra of hydrogen gas with spectroscope having high resolving power. More spectral lines was observed. A theory laid by Sommerfeld was used to explain these new spectral lines. Electrons do not take circular paths but also elliptical paths. The elliptical paths were restricted by the integer k, which could take values from 1 to n, such that n divided by k equal to length of major axis divided by length of minor axis. When k becomes equal to n, then the ellipse becomes a circle. Therefore, there is at least one circular path in every principal energy level. You see that as the value of k increases, the path becomes more and more circular. At lower value of k, the electrons get more penetrated towards the nucleus. The angular quantum number is related to k like this: L equal to k minus 1. The angular momentums in the elliptical paths were given as L square equal to h bar square L plus 1. The angular quantum number L therefore can have values ranging from 0 to n minus 1. These are also designated by the letters S, P, D, F and so on. After F, it follows the alphabetical order. Actually, these letters were taken because in early studies of spectral lines of alkali metals, the lines were termed as sharp, principal, diffuse, fundamental by spectroscopists. So primarily, the azimuthal or angular quantum number specifies the shape of the orbital and was called subshells. The energy of these subshells in multi-electron atoms differs by a substantial amount. Here this energy equation shouldn't have Ze, which is the nuclear charge, because of the shielding effect of inner electrons. So this Z should be replaced by Z effective. The s orbital penetrates most, therefore it cannot be shielded effectively. Consequently, the Z effective of s orbital will be greatest among the subshells. Therefore, its energy will be least. In fact, the energy of a subshell depends both on principal quantum number n and angular quantum number L. It has been found that lower the value of n plus L, the lower will be its energy. The maximum number of electrons in a subshell is 4L plus 2. Number 3. Magnetic quantum number. This describes the orientation of subshells under the influence of external magnetic field. The splitting of spectral lines in the magnetic field is known as Zeeman effect. Actually, an electron is a moving charge and all moving charges behave like magnets. We know that angular momentum L equal to h bar root over L plus 1. Magnetic quantum number ML quantizes the Z component of this angular momentum such that Lz equal to ml h bar. Now let us draw the z-axis. This is the angular momentum vector L, which is equal to root 6 h bar when L equal to 2. In the presence of a magnet, this line is split into quantum restricted angles like this. This gives rise to magnetic quantum numbers from plus 2 to minus 2. Thus we see that ml can have integral values ranging from minus L to plus L. That is, when L equal to 0, ML equal to 0, when L equal to 1, ML equal to minus 1, 0, plus 1, when L equal to 2, ML equal to minus 2, minus 1, 0, plus 1, plus 2, when L equal to 3, ML equal to minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. Each spatially oriented path is called an orbital and can have maximum 2 electrons.
In the absence of magnetic field, these orbitals are of same energy and are called degenerate orbitals.
Number 4. Spin quantum number. Just like the Earth and other planets in the solar system, an electron has two motions. The other motion is spinning motion, which produces another magnetic field. The spin angular momentum is characterized by a quantum number s equal to half for electrons. The intrinsic spin angular momentum is written like this: s equal to h bar root over s plus 1, which is equal to root 3 by 2 h bar. Now let this be the z-axis and this the spin momentum vector. See what happened under the influence of magnet. The component along z-axis is this. This gives sz equal to ms h bar, where ms is the spin quantum number and clearly have two values only. Here, ms equal to plus half is designated by up arrow and is called spin up, or minus half designated by down arrow and is called spin down. In an orbital, the two electrons will have opposite spin. Now let us come to the shape of the orbitals. According to Heisenberg's uncertainty principle, it became impossible to know both the position and velocity of an electron with certain amount of accuracy. Therefore, the concept so far of stationary paths and orbits had to be rejected. The wave character of moving electrons was taken into account by Schrodinger and formed a wave equation by partial differentiation method. The equation was like this. This was called the time-independent Schrodinger wave equation. And this symbol is the Hamiltonian operator. This Hamiltonian operator contained both kinetic and potential energy terms. The solutions of the equation came up with a number of wave functions or energy levels. Each of them was characterized by a set of three quantum numbers: the principal quantum number n, the angular quantum number L, and the magnetic quantum number ML. These wave functions were called atomic orbital. In physics class, we have learnt that intensity of a wave is proportional to the square of the amplitude. Here also, the probability of finding an electron at a particular position is proportional to xi square. The value xi square at different points within the atom predicted the shape of an orbital. After plotting xi square in a three-dimensional coordinate system, where the origin is the nucleus, we get a figure like this for 1s orbital. There has to be a boundary surface to predict the actual shape for the orbital. Boundary surface was taken in such a manner that xi square was constant all over that surface, and inside that boundary surface the probability of finding the electron was 90%. 100% was not taken because that would have made the orbital shape very big. In fact, total atomic volume would have been equal to the orbital volume and shape of all orbital would become the same. Nodes are surfaces where xi square becomes 0. There are two types of nodal surfaces in an orbital. Number 1, radial nodes. The number of radial nodes is n minus L minus 1. Number 2, angular nodes. The number of angular nodes is L. Now on this basis, the orbital shapes are as follows.
See the 1s, 2s and 3s orbital. Here L is 0. Therefore, there is no angular nodes or what is called nodal planes. In 2s, there is one radial node, and in 3s, there are two radial nodes. Now see the two p orbitals. They have no radial nodes. Each of them has one angular node or nodal plane. In the 3p orbitals, there is one radial node and one angular node in each of them. Now let us see the 3d orbitals. There is no radial node, but there are two angular nodes because L equals to 2. Here is the first one and here is the second one.